So in the previous lectures, we talked about two special cases in two-dimensional motion. One is uniformly accelerated two-dimensional motion. The other is circular motion. Now, when it comes to uniformly accelerated two-dimensional motion, perhaps one of the most prominent examples is what's called projectile motion. Projectile motion and free fall, which we studied in chapter 2, are very much alike. They're both powered by gravity. So A equals G, the acceleration gravity. You can think of free fall as a special case of projectile motion, which is that it moves only up and down in a vertical direction. Okay. Now, what if you throw something into the air and it both moves vertically and horizontally? Then the motion becomes two-dimensional, right? And this is what we're going to focus on in this lecture. Now, there are many real-life examples of projectile motion, at least very close approximation to projectile motion. If you really want a true projectile motion, you have to remove all the air because then there will be no air friction. But in many cases, air friction doesn't play a very important role. I mean, you're not talking about a plane flying a paper airplane or something, right? So if something is relatively heavy and compact, then the weight is far more important than air resistance. Then we can say it's approximately a projectile motion. For example, you can see here in this picture, this stunt motorcycle driver. When he's airborne, his body and his motorcycle both will map out a curve that is pretty close to a projectile because the air resistance is not very important. Okay, so if I draw the curve mapped out by his bicycle, you can see it's pretty much a projectile. And same thing happens for this diver. Now, when the diver is airborne, you look at the trajectory of the diver. That is pretty much, again, a projectile. And even this water fountain, I mean, if you look at the drop of water, airborne, it pretty much follows a projectile motion. So the entire water jet maps out a projectile like this. So this is pretty close to projectile motion. This is pretty close to a projectile motion, and so on. Of course, this basketball, same story. Okay, so there are many, many examples of good approximations to projectile motion in the real world. So how do we study that? Well, you recall that we follow the strategy that we said we're going to follow, and that is we're going to break down the motion into two directions. Okay, for two-dimensional motion, break down to x direction and the y direction. And especially if you know the acceleration is uniform in a certain direction, you're gonna put one of the two axes, either x or y, along the direction of the acceleration. So there is no acceleration in the other axis, which means the velocity will be constant. Okay, so you will have uniform accelerated motion in one direction and constant uniform motion in the other direction. And you can study both motions using our knowledge of chapter 2, one-dimensional motion, and then we can recombine them to get the whole picture. So that is the strategy we're going to follow. See this soccer ball being kicked by this player, and when it's airborne, it's a two-dimensional projectile motion. And here S is the overall position vector of the soccer ball at a certain point, and S has two components, x and y. You can write x equals xi plus yj, right? Recall from chapter 3. Now, in order to find the information about S, I can find x first, then I find y using what we know about one-dimensional motion for x and y. And then we put them all together, we can get a whole picture, S, which is xi plus yj. And if you know S, you can find the velocity, you can find everything else you want to know. Okay, so that is the strategy we are going to follow. So in our case, we have a projectile, right? We have a projectile, and for simplicity, let's say it starts out, I threw something out, it leaves my hand at this point, which I designate as the origin of a XY coordinate system. And it doesn't have to start from the origin, but that is the assumption that I make here to make my job easier. Now, I designate an X direction to be horizontal, a Y direction to be upward, and vertical. It doesn't have to be the case, but that's typically what we do. Okay, now, this red curve is projectile. We know common knowledge tells us this is a parabola, but we're going to derive that. Okay, what's given is the initial velocity. It makes an angle theta from the horizontal direction. And we want to know everything about this, this projectile motion. We want to know, for example, the height h attained. We want to know the horizontal range. Okay, you notice that when we drew this horizontal range, we assume that it lands at the same horizontal height as the initial position. Okay, so it doesn't land upstairs or downstairs. It doesn't have to be the case, but that's how we define R in our case. You also want to know T, the time of flight. Okay, the time of flight, among other things. So let me write down what are some of the common questions we want to ask about this projectile motion. So what is H? What is R? The range. What is T? The time of flight. What is the shape of this curve that is Y as a function of X? What function is it? Dot, 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 many other questions. So how do we answer these questions? Well, again, we look at the motion X direction and Y direction separately. Okay, in the X direction, let's see what we come up with. In the X direction, is there any acceleration? No, because the acceleration is vertical and we choose the vertical direction as the y-axis. Okay, so there is no acceleration in X direction. We know that a sub x equals 0. That's what we start with. And a sub y, on the other hand, is negative g. Now, why negative? Because here g is defined to be the magnitude of the acceleration of gravity, 9.8 meters per second squared. Okay, it's a magnitude, it's a positive number, but the actual acceleration is downward. Okay, g is downward. That's g, downward. So it's along the negative x-axis. That's why we have a negative sign here. Right? If you choose the y-axis to be downward, then you won't have that negative sign. So once we know A, what do we do next? Well, we know we can integrate A to get what? To get V. And then we can integrate V to get what? To get X and Y, right? So that's what we're going to do. So the next thing we want to know is what is Vx, what is Vy? What is Vx and what is Vy? Now, in the X direction, if you look at the shadow of this object in a free fall, look at the shadow here. Here's the shadow right here, okay? So as the thing is airborne, it sails through the air, what happens to the shadow? The shadow moves along the x-axis. Does it accelerate along the x direction? No, because the acceleration is vertical in the y direction. So the shadow moves at a constant velocity equal to the initial velocity in the x direction because it never changed. Okay, what is the initial velocity in x direction? So, well, you have v naught and you have this angle theta. Okay, the initial velocity is the component along the x direction. So initial velocity in the x direction is v naught times cosine theta. Okay, v naught times cosine theta. That is the initial value. And this number will not change because there is no acceleration to change it. So that's it. Okay, that's it. Now, Vy. What is that equal to? Well, in the y direction, there is an acceleration, which is the acceleration of gravity. So if you look at the same object and look at the shadow, it drops on the onto the y-axis. The shadow will go up first while slowing down, and will reach the top point right here. The shadow reaches the top point right here, and it could just stop momentarily, and it's go back down while getting faster and faster, right? It is a uniformly accelerated motion, and if you look for the velocity in a uniformly accelerated motion, the generic formula you recall from chapter 2 is what? V equals V naught plus AT, right? V naught here is V naught in a y direction, so it is equal to V naught times sine theta, and it's positive because I'm assuming you throw it upward, so the angle theta is above the x-axis. So the initial velocity in the y direction is V naught sine theta, positive. And the next term is plus AT. This A is A sub y, which is negative g. So don't forget, it is negative gt. Okay, negative g is A in the y direction. So we went from A to V, and then what do we do next? Well, the next step is to find the displacement, x and y, the position vector, x components, x and y. So what's x equal to, what's y equal to? That's the next thing we want to know, right? Well, in the x direction, again, there is no acceleration. So it's uniform motion, and I have x equals vt, right? For uniform motion, v is the component along the x direction, and we know what that is. That is v naught cosine theta again, times t. Okay. Now in the y direction, there is an acceleration. So how do you find the velocity? The displacement for uniformly accelerated motion? Well, the generic formula we learned from chapter 2 is x equals x naught plus v naught t plus 1/2 at squared. Okay. X now it becomes y. So you have three terms. X naught becomes y naught. Y naught is the initial position, but it's right here 0. So there is no y naught here in our case. The next term is v naught t. V naught is in a y direction, so that is v naught sine theta t. That's the next term. And the final term is 1/2 at squared. A is a sub y, which is negative g. So it's minus 1/2 g t squared. So you see, we went from a to v to x or r using components. All these formulas we have learned from chapter 2. All we have to do really is break down, when you see a velocity, break down the x direction, y direction. Okay, the initial velocity. And then we can write all these results without inventing the wheel all over again. And I can tell you, as you will see, everything that you ever want to know about this projectile motion can be found from these results. Okay, I'm going to label them by giving them equation numbers so you can easily refer back to them. So we're going to call this equation 1, 2, 3, and 4. Okay, those are the results. And from these 4 equations, we can find everything we want to know. For example, let's go back to see what we want to know. We want to know h, the height. Okay, how would you find h? How do you find h from these equations? Okay, from these equations. Well, h is the vertical distance attained, vertical height attained. So clearly we have to look at what happens in the y direction, right? And that is either equation number 2 or equation number 4, right? Now, you're looking for the height, which is a displacement. So clearly that leads to equation number 4, because that is the vertical displacement. But equation number 4 is the vertical displacement for any moment t. You're not looking for any moment. You're looking for this particular moment which reaches the very top of the path, right here. Okay, the very top, right here. So what's so special about this point? What is the time t it takes to get to that point? Well, you have to know what's special about that point, right? If you look at the vertical motion, the velocity starts from a certain value in a vertical direction. And as it goes up, it slows down, right? It slows down, slows down, slows down. And when it reaches the very top, what happens in the vertical direction in terms of velocity? It becomes 0, because if it doesn't stop moving up, if the vertical velocity is not 0, that means it's still climbing, right? It hasn't reached the maximum height yet. So when you reach the maximum height, you're no longer going any higher, and therefore you have stopped. So that means Vy is equal to 0 for that particular moment. So that tells me how to find t when you reach the very top. Once you know that t, you can plug that t into equation number 4. You can get that y value, which is equal to h. So let's see if we can find the height. Okay, so we start from equation number 4, but in order to use that equation, we have to know what t is, and that in fact is obtained from equation number 2, by setting Vy equal to 0. So find h, the height attained. Okay, so you set Vy equal to 0, which means v naught sine theta minus gt equals 0. And there's a particular solution to that t, and that t is equal to v naught sine theta over g. This is a special t, which I call t1. Okay, so t1 is the time it takes to go up to the top. And once you know that t1, you can plug into equation number 4, and so you get y at t1. H is equal to y at t1, right? For that particular moment, right? And what is that equal to? Well, you just have to plug in the value of t equal to t1, sine theta times t1, right? Then minus 1/2 g t1 squared. Now I know what t1 is. T1 is v naught sine theta over g. So let's plug that in. V naught sine theta times v naught sine theta over g okay? V naught sine theta over G. And that's the first term, sorry. That's the first term. And the next term is 1/2 gt squared minus 1/2 gt squared. T again is T1, which is V naught sine theta over G. You square that. Okay, you just have to combine these two terms, and it turns out the second term, in fact, is 1/2 of the first term. It's very simple to see. And you find H equal to V naught sine theta squared over 2G. This is the height attained, right? This is the height attained. We got that information from these four equations. That's just the beginning of our study of all the parameters from these four equations. Okay, now, is this the only way to find H? Well, what we did here was to find T1 first, right? Find T1 first, and then we found H. But we never set out to find T1. We just found it, it was something we need to do before we can find H. But is there a way to find H without even knowing the time it takes to reach the top? So you start from the beginning here, okay? You start from the beginning here, and you end up at the top here. Suppose you do not know the time it takes to get there. Can you still find H? H really is the displacement from this initial point to the final point at the top, right? What do you know? Well, we know the acceleration, right? Which is the acceleration of gravity. We know the initial speed. We know the initial velocity in the y direction. Do we know the final velocity in the y direction? Yes, we do. It's 0. Okay. Now, suppose you know initial speed, final speed, and the acceleration. Can you find a displacement? Is there a formula for that? Oh, yes, there is. It's not one of those four. All these four formulas are based on time, except the first one because there's no time. Vx doesn't change, but all the other three depends on time. But there is a formula for uniformly accelerated motion, which we learned from chapter 2 that has no t in it. And that formula is v final squared. You recall from chapter 2. V final squared minus v initial squared equal to 2ax minus x initial. Remember that? But that's exactly what we can use here. If we do not want to know anything about T1 to get the answer for H. We're going to set the final point to be at the top of the path where V equals 0. Okay, so V equals 0. And the initial, we're going to set at what? The beginning point. Remember, everything is the y direction, so we're looking at V naught in the y direction. That's V naught sine theta. You square that. What is that equal to? 2a x minus x initial. A is in the y direction, it's negative g. Okay. X minus x initial is y minus y initial. Okay. Y is the final height. Y naught is the initial height, which is 0. So the difference is just h, isn't it? Right? Now, there are two negative signs, one on the left-hand side, one on the right-hand side. They cancel out. You move that 2g down to the other side. You get h equal to what? V naught sine theta squared over 2g. Isn't that the same as what we already got? Right? So this second method gets you the same answer for h, except it's faster. Why is it faster? Because there's no T1 that you need to solve. Okay? So you look at these different methods. I really encourage you to compare these different methods. They are very, very important. It's very important for you to establish this habit of trying to solve the same problem with different methods, different approaches, and come up with the most efficient answer. So next time you see something totally different, even though the scenario is totally different, the methods that can use to solve them might still be the same, and you can even figure out easily which method is better because you have done this research before. Okay, so that's how we learn something general out of each sample problem. So that's H. So what do you want to do next? We want to find. Let's find R, the range. Okay, so let's find the range. So I'm going to use a different color for that. Let me find the range. R. The range. Now the range is horizontal motion, r. Okay, if you look at r here, that's how r is defined. It's from here to there, that's r. Okay, so it has to do with horizontal motion. And if you look at the horizontal equations, that would be equation number 1 and number 3, right? Now, clearly, we're looking for displacement. So it's equation number 3 we should be using if you want to use one of these 4 equations. But again, we have a problem. The problem is we don't know what t is. That t is a total time of flight, right? From beginning to the end. If we know that time, we can figure out x. Just plug that in. So instead of finding r, let's find t first. Okay, let's find t first. So I'm going to find t first. Find t. The time of flight. How do you find the time of flight? Which one of these 4 equations do we use now? Well, it's about how long the thing can stay in air, right? It goes up and it goes down. As soon as it gets back to the same horizontal height, the game is over, right? This is the same height as when it started, right? So you certainly want to look at the y direction. What is so special when the thing lands here? What's so special when the thing lands? Do we know its final speed from scratch? No, we don't. Do we know its final x movement, which is r? No, we don't. Actually, we set out to find r in the first place, right? What do we know about this point for sure? Well, then one thing we know for sure. We know that when you reach that point, y equals what? Y equals 0. Okay, so clearly, if you want to find the total time of flight, you better use equation number 4, because that tells me y as at any moment. What if you set y equal to 0? When you set y equal to 0, you're going to find that time it takes to get there. So I'm going to use equation number 4. Okay, so set y equal to 0, not vy, but y. Set it equal to 0. Which means that v initial sine theta t minus 1/2 gt squared. I want to set that to equal to 0. This is not just any t, okay? It's the total time of flight. Now, you notice that this is a quadratic equation with 2 solutions, t1 and t2. One of the t's is 0, okay? Right? 0 and 0. But that is useless because that only means this moment right here at the very beginning of the launch. This moment right here. Okay, of course t equal to 0 and y is also equal to 0, but that's not what we're looking for. We're looking for the other moment. Looking for this moment. Okay, we're looking for this moment. So in our case, t is not equal to 0. So we can cross on the 1 power of t because it's not equal to 0. What we're left is the other t, which is v naught, which satisfies v naught sine theta minus 1/2 g big T equal to 0. I already crossed out 1 power of t. Okay, this is the time of flight. And you can easily find t now. T equals to what? V naught sine theta. There's a 2 here over g. This is the time of flight. Okay, this is the time of flight. I'm going to highlight it as an important result. And if you compare this big T with T1, remember T1 here? Okay, this is T1 here, right here. And compare with big T, you'll find they're the same, except we have an extra factor of 2 here in the capital T. What that tells you? It tells you that it takes the same amount of time going up and going down. That's why the total time of flight is double T1. Okay, is that a coincidence? Is that something understandable? Well, I mean, intuitively it makes sense, right? I mean, you go up and go down, take the same amount of time going up and same amount of time going down. Can we understand this phenomenon from physics, not just from the math, which gives us the result? Why does it take the same amount of time going up and going down? Well, actually, there are ways to understand why that's the case. If you look at up and downward motion, okay, they certainly cover the same distance, right? Going up and going down, both cover distance h, right? If you can also show that they have the same average speed, you cover the same distance with the same average speed, you're going to have to spend the same time, right? Does it have the same average speed going up and down? Well, remember, for uniformly accelerated motion, the average speed is initial speed plus final speed over 2. I'm assuming the speed doesn't change direction, okay? Then, initial speed plus final speed over 2 is the average speed. Going up, initial speed is v naught in the y direction, v naught sine theta, and the final speed is 0, right? So the average speed is just in half of the initial speed. So half of v naught sine theta. Now, going down, the initial speed is 0. The final speed is something we don't know yet. But if the final speed going down right before it hits the ground, if the vertical component of the final velocity, if the magnitude equals to the vertical component of the initial velocity going up, let's say initially it has upward velocity of 10 meters per second, and finally, right before it lands, it has the final downward velocity of 10 meters per second, then isn't it true that going up, the average velocity will be 5 meters per second, and going down is also 5 meters per second, right? Then you would prove that they have the same average speed, and of course, you also have the same average distance covered, which is h. Then no wonder t1 going up is half of the total time, right? So can we show that the average, that initial velocity going up, okay, which is this, and the final velocity going down have the same magnitude? Can we show that? Oh yes, we can. All we have to do is really compare these two velocities in the right direction. I call one initial state, one final state. I do not know the time it takes to get from here to there. I don't want to use that information at the very least. I don't want to use that. Can I still compare the two speeds or two velocities, knowing only the acceleration and, of course, the displacement? Yes, I can. Same exact formula, v final squared minus v initial squared equal to 2a delta x, except delta x becomes delta y here. We're looking at the y direction, right? What is delta y for the initial and final here? 0, because you land at the same horizontal position, right? So if you compare the, right after it's launched and right before it crashed, delta y equals 0. What did that tell you? It tells you that v final squared in the y direction equals v initial squared in the y direction, because the other side is 2a delta y is 0. Okay, so clearly we have shown that the average speed going up and the average speed going down are equal to each other. No wonder it takes the same amount of time to go up and down. So therefore, the total time of flight is just twice t1, the time it takes to go to the top. Okay, so no matter how you look at it, we've seen it from different angles. We got the same result, and that is this is the total time, twice as much as the time it takes to go up. And once we know t, we can easily find the range r now. The range r. So finally, for the range r, let me find it now. Different color. So r equals to the value of x at t, right? You go back to equation number 4 here. I just plug in big T to replace the generic time t. Then I find actually equation number 3 here, right? You just plug in the big T to replace the generic time, you will get the range. And that equals to v naught cosine theta times big T. Okay, now big T, I copy the big T value, and that is v naught cosine theta times 2v naught sine theta over g. I can easily combine them. I have a v naught cosine theta, and then I have a sine theta. There's a 2 sine cosine in the numerator. 2 sine theta cosine theta is equal to sine of 2 theta, as you learned from your trig class. So r equals to v naught squared sine 2 theta over g. This is the range formula. Okay, this sine of 2 theta has important consequences. For example, if one wishes to maximize the range, to throw the ball as far as possible, what kind of angle should you launch from? What common sense tells us is 45 degrees. Now we can see mathematical proof that it is 45 degrees, because when you plug in theta equal 45 degrees, you get 2 theta equal 90 degrees, and that's how we maximize the sine function, right? So it makes sense. Okay, you see, we've so far found R, found T, found H. All these are important parameters we wish to learn from these equations 1 through 4. Equations 1 through 4. So clearly, as I promised, once you know, use component expressions to find Vx, Vy, X, and Y, I can find everything else I want to know. So what else is on the table? Well, there's this, right? The shape of the curve. Now that's actually quite simple. The shape of the curve is y as a function of x. Now what I have here is y as a function of t and x as a function of t, equation number 3 and 4. I can eliminate t from equation number 3 because it's a linear equation, easy to do. So t equals x over v naught cosine theta. And then I plug that t into the 4th equation, right? Then I don't have any t there anymore. So let's do that. Then we can see the shape of the curve. Okay, so that's called a trajectory equation. Okay, trajectory equation. Let me write that down. That's y is a function of x. Now we learned from equation number 3 that t equals x over v naught cosine theta, which we plug into equation number 4. So now y equals v naught sine theta times t, and t is this guy, is x over v naught cosine theta. Okay, and the next term is 1/2 gt squared minus 1/2 gt squared. And again, t is given by x over v naught cosine theta, and then square that. Right? Let me just clean things up a little bit. So y equals to v naught cancels with that v naught, and sine of a cosine is tangent x times tangent of theta. That's the first term. And then minus 1/2 g x squared over v naught cosine theta squared. You see, I am getting what's expected. I'm getting a squared, x squared term. So y is a quadratic function of x. Okay, let me highlight that as well. Y is a quadratic function of x. And you know from your math class that this tells me that you have a parabola. Okay, it's a parabola curving downwards. Why? Because you have a negative sign in front of the quadratic term. And the reason why we have negative sign can be traced all the way back to here. Ay being negative g, not positive g. It's because gravity pulls you down. That's why whatever you throw something upwards, eventually it's going to come back down because of gravity. So that's why the parabola curves downwards. Okay, so that's the physics here. That's what a negative sign stands for. Otherwise, you got a parabola curving up. That makes no sense. Okay, so we found some of the most important parameters for this parabola, for this projectile motion, from our knowledge of the motion in the x and the y direction. So that is the strategy we've been following, and it's been a success so far. We found all these parameters by combining our information about x direction and y direction. Okay, so next, what I will do is, in the next lecture, is to apply the knowledge that we learned so far from projectile motion to study some more interesting applications, some sample problems.